Hello again, this is Math 1120, remote delivery for April 21st, 2020, and this is part 3. I encourage you to use these buttons to take your time with the video and to perfect your understanding. Section 9.2 in Sullivan's text is about estimating the population mean. This is about point estimates and confidence intervals. Now, it's important that you realize the objectives look about the same. The concepts are the same, including the interpretation of point estimates and confidence intervals, and the big questions to be answered are finding the confidence intervals and what sample size do you need to estimate a population mean. But the details are significantly different because now we're talking about a population mean, and there's an entirely new distribution, the t-distribution, that we'll be talking about. Let's begin. The point estimate of the population mean, mu, is a sample mean, x bar. And once upon a time, a fellow who was working for the Guinness Brewery Company, this was in the early 1900s, was limited to very small data sets, and he also did not know whether the population standard deviation was known. And since he didn't know that, he just substituted the sample standard deviation into this. Now, when he did this, he noticed that the variability was higher, so he developed a model that accounts for additional variability by using S in place of sigma, and you could do this for smaller and smaller data sets. Guinness would not allow Gossett to publish his results, but he did publish them under a phony name, and the phony name was A student. And so this is called the student t-distribution. The student t-distribution does assume that a small sample, perhaps, is taken from a population, but the underlying sample is drawn from an overall population that is a normal distribution. And this is the sample statistic, and this is said to follow a student t-distribution with n-1 degrees of freedom. This is the biggest thing you need to keep in mind. That is that it comes from a normal distribution, and if we're drawing samples of size n, the number of degrees of freedom is n-1. You also use the sample standard deviation instead of the population standard deviation. And the t-distribution has a number of properties that are like the normal distribution. In fact, as n gets bigger and bigger, it gets very close to being the normal curve. It is symmetric, centered at 0, and symmetric at 0. And the area under the curve is 1, and since it's symmetric, the area under half the curve is 1/2. But the t-distribution is different for different degrees of freedom. And the areas in the tail is a little greater than the areas in the tail of the standard normal. This is what the t-table looks like. This is table 7 in your book, and this will be provided for you for the final exam. So let's talk about the table. This is the degrees of freedom that go down this column. And the degrees of freedom are always n-1. So if the sample had 16 data points, then n-1 would be 15. The degrees of freedom would be 15. And the area in the right tail, this area, is what's shown across here. And so what happens is inside here are the critical values that we will be using in finding the confidence intervals. We'll say more about this later. In fact, let's just say a little bit more about it now. So suppose you had a sample that had 16. That means the degrees of freedom is 15. It is always n-1 in this application. So we're going to be looking across the row that is 15. And suppose we wanted to find what value of t separates this area we're showing here of 0.10. So we move over here. This is the area under the right tail is 0.10. So we run our finger down here, our finger across here, And the answer to that would be t of 0.10 would be 1.341. That's how we use this table. Here's how we construct a confidence interval. We take a sample and compute the sample mean and the sample standard deviation, and then the lower bound of the confidence interval is x bar minus t. This is alpha over 2 s, that's the standard deviation, over the square root of n. That is the lower bound. Again, x bar is in the middle, and this is the margin of error. The margin of error is this expression. So it's x bar minus the margin of error. The upper bound in the confidence interval is x bar plus that critical value times s over the square root of n. So these are the formulas you use to construct the confidence interval upper and lower bounds, and this is what we do for determining the sample size required to estimate the population mean with a level of confidence within a specified margin of error. Now, since the t distribution is similar to the normal distribution, we actually use z alpha over 2 here from the normal curve, not t alpha over 2, but we use s, and this is the margin of error. Now, we're about ready to do a couple of examples, and in this example we will talk about a 95% confidence interval. Now, if we do 95% confidence interval, it's symmetric, and we always, for a confidence interval, take the middle 95%. So we have 2.5% here and 2.5% over here. So for a 95% confidence interval, we're going to be looking at 2.5% over here. And the problem that we're going to look at has 12 data points, so that means the degrees of freedom is 11. So I'm going to run my finger over, and I find that for a 95% confidence interval, t, the critical value that I'm going to use is t, and this is 0.025, is 2.201. Also, the same problem asks us about a 99% confidence interval. That means that we're talking about the middle 99%. That means I got 1% over here in, or excuse me, I have a 0.5% over here and a 0.5% over here by symmetry. So on that question, what will happen is, again, I have 12 data points, the degrees of freedom will be 11, but now I'm going to look here because this is the area in the right tail, and we'll see that the number that we're using is going to be 3.106. Okay, so here are some problems that we'll talk about. I'm going to ask you to pause, read this problem, think about it, try to apply the formulas, and we'll see how you do. Let's see how you did. Okay, I have these data points, and it looks like I have 12 of these, so x bar, I need that. So I find the average of those, and you should have gotten 4.893. You also should have calculated the standard deviation of this sample, which is 0.319. I showed you on a previous slide that t of 0.025 is this number, so the lower bound is x bar minus that critical value times, this is s over the square root of n. You get this as the lower bound. The upper bound similarly is going to be x bar plus that critical value, and this is s over the square root of n. So you see that we're 95% confident that the mean is between this number as a lower bound and this number as an upper bound. If we change things to be a 99% confidence, I showed you that the critical value changes to 3.01. So the lower bound, when I do the similar calculation, is 4.607, and the upper bound is, again using 3.106, is 5.176. 0.79. So we're 99% confidence that the mean pH is between those two numbers. That's the confidence interval. And what happens as the level of confidence increases? Well, the margin of error increases as the confidence level increases, because that's the same concept we talked about before. Okay, let's look at another example. I'm going to ask you to pause, read this, try to do it, and we'll come back and look at how you did. Let's see how you did. Now here it is important that we are using z alpha over 2, so these are the critical values. So if we're doing 95%, it's going to be 1.96. If we're doing 99%, it's going to be 2.575. And this is taken from your normal tables. This is at the bottom of your normal tables. I think I talked a little bit about that. So how many subjects are needed to estimate the number of books with a 95% confidence? Well, you need n. It's 1.96. This is s over let's see, oh, this is the margin of error, and the margin of error was within 4 books here. So that was 4, you get 67. If you double the accuracy, that means instead of being within 4 books, you want to be within 2 books. This is the only number that changes. You square it and you round up, and you get 265. So what effect does doubling the required accuracy have? Well, it quadruples, because this number is 1/4 of this number, or this number is 4 times that number, more or less. In part D, we're changing the confidence interval to 99%. This means that for 99%, we're going to be using 2.575, and we put that in, we do the calculation, and we get 115. And so these are some other answers, but increasing the level of confidence increases the sample size that you need. For a fixed margin of error, greater confidence can be achieved by using a larger sample size. Okay, so I have talked a little bit with Linda and liaising with Linda, and so we do have some emerging plans for our end game. Next week I will cover in the televised part elements of Chapter 5, and we'll also discuss within that context the final exam protocol. The final week that we meet, the last week I want to say, prior to final exam week, Linda and I are working to have a study guide for you. I'm going to give Linda the final exam in draft form, and she'll prepare a study guide to help you prepare. Again, the last week prior to final exam week, we're exploring having a Zoom session for Q&A. It will not be mandatory, but it will be held during class time. I didn't write this down, but I'm probably going to see if we can record it, and it will be provided for students to ask questions. And I will also, just because I'm really about teaching you as rich a course as I can, there will be one last set of enrichment content provided via videos, but this part will not be on the final, but it is my gift to you. Okay, so after tonight we have, after tonight we have 2 weeks only of content left. My advice to everyone is to finish strong. We can do this. Linda and I have your backs. Now, more than ever, time is precious. Each day must count. Do the math, it will make you strong. Take care of yourself and each other.